So in this particular example, we're given a circuit that contains a capacitor and an inductor. And then at time t equals 0, those capacitor and inductor gets connected to this part of the circuit in here. And we're being asked to compute what I of t is and what V of t is. That is the current flowing through the inductor and the voltage across that capacitor in here. And we're also given that before switching, the voltage across that capacitor was 2 volts. Basically, the initial condition across the capacitor was 2 volts, and the initial current flowing through the inductor happened to be 1 amp. Okay, so we do not have to compute them. And we're asked to compute the I of t and V of t. So frankly speaking, we can go ahead and write basically replace the switch by a closed switch and write the equations, but it might be just easier to replace this part of the circuit, since I'm not interested in anything happening to it, by its Thevenin equivalent, or maybe even better, the Norton equivalent, since I'll be replacing it with a current source in parallel with a resistor, and it will be in parallel with a capacitor and the inductor. So let's compute the Norton equivalent of this part of the circuit. And the Norton equivalent of this part of the circuit, and I'll just highlight it in here so that you can follow along. This is what I'm after, the Norton equivalent of this part here, from this particular perspective in here, from here, okay? All right, so how do we do that? Well, a couple of things that we need to do. First, you can either replace this here by a short and figure out with the I short circuit, or maybe what we can do is we can figure out with the V Thevenin in here. This is plus minus in here, and that's V Thevenin, which is also the V open circuit, okay? So let's compute it with a V open circuit, because I think it's pretty straightforward and simple. Well, first of all, this resistor in that particular case, because there's no current flowing through it, since this is open in here, doesn't exist. So the voltage in here is the same voltage across the 1 ohm, and it is voltage division. We have a 1 ohm and 1 ohm and 5 volts. So the V open circuit, we can easily just say, well, V open circuit, which is the same as V Thevenin, is just simply 5 divided by 2, which is 2.5 volts. Okay. All right, that's good. What about the R Thevenin? Well, we can redraw that circuit. I'll turn off that voltage source, and what I'll end up with is 1 ohm in here, 1 ohm in here, and this is the voltage source in here. We just turn it off, and then 0.5 ohms in here. And what we're interested in is the R Thevenin seen from here. Well, 1 and 1 in parallel is just simply half, and in series with another half, that means that R Thevenin is just simply 1 ohm. All right, we have everything we need to figure out what the Thevenin equivalent circuit, or maybe I'll compute I Norton, which is the same as I short circuit. It's just simply V Thevenin divided by R Thevenin, and that basically is 2.5 divided by 1, which is 2.5 amps. Okay, so let me redraw that circuit. So now this circuit should be drawn in the following. We have 2.5 amps in parallel with a resistor that is 1 ohm, in parallel with an inductor that is 0.5 henries, in parallel with a capacitor that is 0.25 farads. 0.25 farads. And of course we have some sort of an initial conditions. These initial conditions here, I'll just write them. V0, okay, happen to be 2 volts, and the current in here, which is I0, happen to be 1 amp, and I'm assuming that this is I of t I'm interested in, and this is V of t that I'm interested in. Okay, so I think we have everything we need to write the equation that describes this circuit. This is of course after switching, so I basically replaced that green button, the Norton, and I connected it. That's what I've done. So let me write the differential equation that describes the circuit. So simply we can just say, if this is my reference, we can just figure out what the voltage in here, and this is actually V of t. It's the same V of t in here. So we can just say, well, negative 2.5, let me just write it in blue, negative 2.5 amps plus V of t divided by 1 ohms plus, well, I'm looking for the current, so I'll just keep it as I of t. This is the current flowing through the inductor. And what about this one here? Well, this basically is V of t. I'm actually looking for currents again, so I'm not looking for V of t. What I'm looking is the voltage across the capacitor, and of course the current flowing through a capacitor. So this is I of t is just simply C times dV of t divided by d of t. And based on passive sign convention, if this is plus, this is minus, and I wanted that, it's hitting the positive, so positive is okay. So that here C in this particular case happened to be 0.25 farads. Times dV of t divided by d of t, and that equals 0. So this is the differential equation that describes the circuit, but at this moment it contains the I and the V. I need to write one in terms of the other, and frankly speaking, it doesn't matter which one you pick. I will basically pick to rewrite, I'll keep the I of t and I'll rewrite the dv and v and so forth in that term. Well, we already figured out the I of t. Well, I'll keep the I of t. So let's do it that way here. So what I will assume is v of t is just simply L times di of t divided by d of t. So let me just double check. What we have is a v across the inductor, and it's simply L, which is, in our case, I'll just write it right away, it's 0.5 henries, okay, times the current flowing through the inductor, and we're assuming I is the current flowing through the inductor, so this is correct. So now we can replace this with that, but also what we have is dv of t, so what we need to do is we need to tell me, well, dv of t divided by d of t is just simply 0.5, the second derivative of I divided by d of t squared. Okay, so I'll take these two in here, I'll just substitute them in this equation, and what I will get is v of t is just simply 0.5 di of t divided by d of t plus I of t, I'll keep that, plus 0.25 dv of t, so I'll have to multiply by 0.5 in here, di squared of t divided by dt squared, and that equals 2.5. What I've done is I just moved this to the other side. Alright, so we clean it up with a little bit of algebra, and I will end up, I want to make sure that the coefficient for the second derivative of I is 0, and what I will end up with is the following: di squared of t divided by t squared plus, I believe that will be 4 di of t divided by d of t plus 8 I of t equals 20, and that is the differential equation that described this particular parallel RLC circuit. Okay, so now we can proceed by solving this equation. So now this here is not equal to 0, so the solution for this particular circuit, I of t, will happen to have two parts, and it will have a particular solution, okay, and a complementary solution. That's what it will have. So let's try to figure out what the particular solution is. We know the particular solution is based on the forcing function. The forcing function is constant, so that means the particular solution should be constant. So the second derivative and the first derivative will be 0. So we can compute it. So I p of t is just simply, the way we compute it is 0 plus 8. I particular solution equals 20. That means the I p of t, that's the particular solution, is just simply 20 divided by 8, and that's equal to, I believe, 2.5 amps. All right, everything is in ohms, yeah, so that must be amps. Okay, good. So that's the that's basically the particular solution. What about the complementary solution? Well, the complementary solution is based on the homogeneous equation. That's the second derivative of I of t plus 4 times the first derivative of I of t plus 8 times I of t equals 0. So that's the homogeneous equation. We'll end up with the characteristic equation of s squared plus 4s plus 8 equals 0. We can just basically say, well, 2 alpha is just simply 4. That means alpha is 2. Well, omega 0 squared is 8. That means omega 0 is just simply the square root of 8. And the square root of 8 is just, I believe, 2.83. which means that alpha is less than omega 0. That means what we have is an underdamped response. Of course, you could have computed the discriminant, delta, and you would have basically gotten also a negative number, which is 4 squared minus 4 times 1 times 8, and that as 4 squared, which is 16 minus 24. Or minus 32, not 24, because 4 times 8 is 32. Okay, so that will be 4 squared minus 4 times 8, and that will become negative 16. Okay, so it's a negative number, so I have an underdamped response, so there's some sort of an oscillation and so forth. We can go ahead, we know that it's an underdamped. What we need to do is we need to compute the omega d. Okay, so omega d is just simply omega 0 squared minus alpha squared, and that basically is omega 0 squared is just simply 8 minus alpha squared, which is 4. That is 2. Okay, that's rad per second. By the way, everything is in rad per second, so even the alpha here is rad per second, and this is rad per second, radians per second. So I think we have everything to compute our particular solution, so the complementary solution. So the complementary solution I of t is just simply e to the negative alpha, which is 2 of t, beta 1 cosine omega d, which is 2 of t, plus e to the negative 2 of t, beta 2 sine omega d, which is that here. So that is it. So let me just highlight it in here. So that is the complementary solution, and I believe we figured out what the particular solution is, and we said that the particular solution is 2.5. We just have to combine these two together, and what we end up with is I of t is just simply 2.5 plus this equation in here, which is e to the negative 2t beta 1 cosine 2 of t plus I believe e to the negative 2t beta 2 sine 2t. Now what we need to do is we need to use the initial condition to find what b1 and b2 are. And remember, the initial conditions here are given to us. So I'll just recopy this one here. Okay, so they're given to us. We don't have to compute them as per se, because we know that v0 is 2 and we know that i0 is 1. In this particular case, I need i0. So what I can say is i0, I know it's 1. It's just simply 2.5 plus e to the power 0, which is 1, beta 1 cosine 0, which is 1, plus e to the power 0, which is 1, times beta 2 times sine of 0. Well, sine of 0 is 0. That means the whole thing here will be 0. So that's it. Well, I'll replace the I of 0 by its value. Well, I of 0 is simply the following, which is 1. Well, okay, I think we have everything we need to compute what beta 1 is. So beta 1 is just simply negative 1.5. Okay, so we figured out beta 1. Let me just highlight it. Okay, so we'll do that here. Now what's next? Well, what's next is to figure out what beta 2 is. What do we need to do? We need to figure out what di of t divided by d of t. Well, we know that v equals L times di of t divided by d of t. This is actually the voltage across the inductor. Okay, so we know that di of t divided by d of t equals 1 divided by L, and that's here times v of t. Okay, so we can just simply say this is 1 divided by L, which is 1 divided by 0.5. Well, 1 divided by 0.5 is just simply 2, so we can just replace it by 2. Okay, v of t. So if I said that I want this to be t of 0, that means I'm substituting this by v0. And the v0, since it is the same v0 in here, which is 2, that means we can say that this here is 4, because 2 times 2 is 4. So we know what di of t divided by d of t. So all you have to do now is just go to this here, take the first derivative, actually this one here. It doesn't really matter because you can take the derivative of 2.5, it's going to be 0. So you take the derivative of 2.5, it'll be 0. And then you take the derivative of this, and you'll end up with an equation that contains beta 1 and beta 2. Or you can take a look at my notes, and in the notes I provided that the equation in that particular case is the following. di of t divided by d of t at t equals 0 is simply for that particular solution is negative alpha beta 1 plus omega d beta 2. So what do we have? We have this to be 4. Do we know the alpha? We know it's 2. Beta 1, do we know beta 1? Yes, negative 1.5. Do we know omega d? Yes, it's a 2, and that's beta 2. That means beta 2 is just simply 0.5. Okay, so now what we have to do is just combine everything together. These here becomes I of t is just simply 2.5 plus beta 1, which is actually negative 1.5 e to the negative 2 of t cosine 2 of t plus 0.5 e to the negative 2 of t sine 2 of t, and that's an amp for t is greater than or equal to 0. So that's basically what we've been looking for. That is the current through the inductor. All right, so a quick sanity check in here. What is the inductor initially? So if I substitute t equals 0, this goes away. This is 1. This is 1. So I'll get 2.5 minus 1.5, and that's 1. And that's exactly what we have. We have 1. What if we wait for a very long time? So for a very long time, the e in here and the e in here will go to 0, so the whole thing here goes to 0. So that leaves me at 2.5, which makes sense because that 2.5 just go through that because the inductor is just simply a wire. All right, so we're not completely done because we're also being asked to compute what v of t is. But if you think about it, well, we know what v of t is because we can just use this here. So v of t is simply L, which is 0.5 times di of t divided by d of t. And so all you have to do is just take the derivative. Well, the derivative 0.5 will be 0. Then you take the derivative and the derivative of this, the product rule. And what you will end up with is the following. V of t should be equal to, of course, the L will be multiplied by, well, L is 0.5. I wrote it, 2 times e to the negative 2 of t. This is equal in here. Cosine 2 of t plus e to the negative 2 of t sine 2 of t. And that's volts for t is greater than or equal to 0. Again, let's do a quick sanity check in here. What if we substitute t equal infinity? If you substitute t equals infinity, both of them should be 0, and the voltage across this will be 0, which is good because that's a wire, so the voltage across it is a 0. What if I substitute t equals 0? This part here is 0 because the sign is 0. This part is 1, this part is 1, so I'll end up with 2, and that's exactly what we have. We have 2. So I believe these are the two equations that describe this particular RLC circuit. We can do a few plots in here just to see what's happening. So right before switching, what do we have? Well, we have the current through the inductor is at 1, and that's what we see in here, that's 1. And what does it do? It's trying to reach 2.5, that's what we saw. This is the 2.5 in here, so that's the 2.5. But because of the oscillation of the cosine and sine, it overshoots a little bit in here, and you can see it actually exceeds 2.5, and then eventually it settles to the 2.5. Similarly, what we do here is we start at 2 volts in here, and our ultimate goal is to reach the 0, which we do. And because of oscillation, you'll see it overshoots as well, or undershoots here, and you can see it in the negative as well.